Hi, this video is about buffer solutions. If you're in the Brown and LeMay textbook, we're in chapter 17 and we're in the second section. So what exactly is a buffer? Well, by definition, a buffer is a solution that has the ability to resist changes in pH. So if you add an acid or a base to a buffer solution, it's able to pretty much stabilize the pH. It won't change very much with the addition of those acids and bases. So what is the recipe for a buffer? Well, the recipe is you need to have a weak acid and its conjugate base in solution, or a weak base and its conjugate acid in solution. Now, a buffer works by having an acid available to react with any hydroxide ions that are added. So if you've got a buffer and you add a base to it, the acid portion of the buffer will neutralize the base. But it also contains a base, so that if you add anything that can produce hydronium ions or H+ ions, that base will react to neutralize those ions. Now, if you've got an acid and a base in a buffer, you don't want them to react with each other. So that's why you use conjugates. You use a conjugate acid-base pair of a weak acid or a weak base. Now, here are some examples of a buffer. You could have acetic acid, that's a weak acid, and its conjugate base acetate. And so the form of the conjugate base would be in the form of a salt, so sodium acetate. Remember that sodium won't do anything. You could also have ammonia, that would be the base, and the ammonium ion would be the conjugate acid of ammonia. The chloride ion isn't going to do anything to the base, to the pH, because the chloride ion is the conjugate base of a strong acid, which makes it not really a base at all. It's a base that's weaker than water. So let's talk about something you might hear about, especially in biology. It's called buffer capacity. And it's the ability of how much that buffer can resist these changes in pH. So the best buffer is made when the concentration of the acid and its conjugate base are fairly similar to one another. And if you have even like larger concentrations of acid and its conjugate base, the more buffering capacity it has, because you've got more acid and base available to react with whatever you add to it. Okay, so let's go ahead and have you select solutions below that are a buffer. Potassium hydrogen phosphate and phosphoric acid. Is that a buffer solution? The answer is yes. Phosphoric acid is a weak acid, and hydrogen phosphate is its conjugate base. So yes, it meets the criteria for being a buffer. What about sodium perchlorate and perchloric acid? Are these buffer? Would this make a buffer solution? The answer is no, and the reason the answer is no, yes, we have an acid, but it's a strong acid, it's perchloric acid, and there's really no base in this solution because the perchlorate ion, the conjugate base of that strong acid, isn't really it's not really a base at all. It's a base that's weaker than water. So because we have that strong acid, its conjugate base is not going to be much of a base at all to do much in a buffer. So that second solution is not a buffer. How about the third? Potassium fluoride and hydrofluoric acid. Is this a buffer? The answer is yes, because hydrofluoric acid is a weak acid, and the fluoride ion is it's its conjugate base, and it's a good base. Okay. And finally, the last one is potassium bromide and hydrobromic acid. Is this a buffer solution? The answer is no. Hydrobromic acid is a strong acid, so that could definitely neutralize any base that you added, but there's really no base in this buffer at all because the bromide ion is a base that's weaker than water because the conjugate base of strong acids really aren't basic at all. All right, so now that you know how to recognize a buffer and you know the recipe for a buffer, now we can calculate the pH of a buffer solution using this really helpful equation. It's called the Henderson-Hasselbalch equation. And if you have a buffer, the pH is equal to the pKa, should be pKa in that, plus the log of the concentration of the base over the concentration of the acid. So whenever you have a buffer solution, you can use this equation, and it works really, really well. However, there's some things I want you to notice about it. If the concentration of the conjugate base and the weak acid are the same, so that is when you're halfway to your equivalence point, it would be the log of 1, and the log of 1 is 0. So when the concentration of the conjugate base and the weak acid are equal, you're halfway to your equivalence point, and the pH is equal to the pKa. It's worth remembering that. So here is a calculation where this is the case. It's asking you to calculate the pH, and they're really nice in this question because they say have a buffer system. A lot of times they don't tell you you have a buffer, you just have to recognize it. It's 1 molar acetic acid, a weak acid, and 1 molar sodium acetate. The sodium does nothing. The acetate is the conjugate base of that weak acid, acetic acid. Because the acetate ion concentration and the acetic acid concentration are the same, the pH of this buffer would be equal to the pKa of acetic acid. And so you look up the Ka for acetic acid, and it's 1.8 times 10 to the negative fifth. Take the negative log of the Ka, and that gives you the pKa, and that gives you a pKa of 4.74. And so the pH of the solution would be 4.74. So let's just have a brief look at a titration curve. In this titration curve, you can see where there is this very, very steep slope right here at the equivalence point. It's very important to see and to know that there's a steep slope here. And we see that our pH is at the equivalence point is above 7. So this would have been a weak acid, strong base titration. And so if we started off with a weak acid down here, as we add base to it, we would be producing its conjugate base, and until we get to the equivalence point, we still have weak acid in solution, and now we're making its conjugate base. So this region in here, it's kind of flat. The pH is not changing much. This portion of the curve is a buffer. So it's just important to know where in a titration curve you have a buffer and how this region of the graph really fits the definition of a buffer. It's resisting changes in pH. It's not changing much at all by the addition of the base that you're adding here. So that is buffers in a nutshell. Know when you have a buffer, know the recipe for a buffer, and know how to use the Henderson-Hasselbalch equation.